So when dealing with atoms, if this atom and this atom are about to collide, the kinetic energy before the collision will still be equal to the kinetic energy after the collision. So kinetic energy of all objects before the collision is equal to kinetic energy of all objects after a collision, provided we're working with really small things like atoms. And we refer to these collisions as elastic collisions. Elastic. And elastic collisions usually only happen at the atomic level. But in regular collisions involving regular sized objects, so for example, two cars, the energy will not be conserved. In these cases, you'd probably measure that the kinetic energy after the collision is lesser than the kinetic energy before, and we would refer to it as inelastic collisions. The reason for this is because the kinetic energy might have been lost in, like, if these two cars collide, they're probably gonna explode, and that would count as heat, sound, light. So so kinetic energy can be lost in many different ways, including an explosion, or in other words, heat, sound, light. Because to produce heat or sound or light, you have to use energy. Now, if the change is really small, if two pool balls, so like red pool ball and purple pool ball, bounce off each other, then the change is pretty small. The lost energy is pretty small. But if it's let me draw a rock, and then someone decides to shoot a bullet into it, and then the rock just shatters, that is a big change. The energy lost is very great. But conservation of the momentum, not the energy, but the momentum is always conserved. So in elastic collisions, the energy is conserved, and the momentum is conserved. But in inelastic collisions, the energy is not conserved, but the momentum will be conserved. So what we want to do first is figure out the velocity of the block as a few seconds after impact, and we know that the kinetic energy for the block once it is affected is equal to the potential energy once it reaches its maximum height. So 1/2 mv squared is equal to mgh. The mass of the wood block is the same in both scenarios, and then we can just solve for the velocity, making it v is equal to root 2gh. So v would be equal to 2 times 9.81 times the height, which was 0.386. And this gives us a velocity of 2.75 meters per second. So now we know this, so let's use conservation of momentum to solve for velocity of the bullet, which I should draw in blue, so that makes our life a lot easier. And here's what we should also note. When the bullet hits the block, it actually gets wedged in the block. So if you watched my previous video before this, you would know that if they're sticking together, let's just add up the masses. So 5.75 kg plus 0.02, 5.77, and the velocity will be 2.75. So these are the before conditions of the momentum, and these are the after conditions. So let's get the mass of the bullet, 0.02, the velocity we don't know, plus 0 because the block is at rest, is equal to 15.8788. And then we divide both sides by 0.02 to isolate the velocity, and we get 79 Well, let's actually see. Yes, 3 significant figures. This works. So now we have to determine if the collision was elastic or inelastic. So this is 1/2 mv squared plus 1/2 mv squared is equal to 1/2 mv squared. So this will be the bullet, this will be the block, and then this will be the bullet and block wedged together after the collision. So now we're dealing with the conservation of energy. Everything before the equal sign is before the collision, everything after is after. The mass of the bullet, 0.02, times the velocity of the bullet, which we have just calculated, divided by 2, plus 0 since the ball is at rest. So let's go here. So like 6304.36 is equal to 1/2 mv squared of the ball of the block and bullet wedged together. So 5.77 multiplied by the velocity of the block, which was 2.75 squared over 2. And this gives us like 21.8 joules. So clearly, if the total kinetic energy after the collision is 21.8, this is very inelastic. We lost so much energy.